All right, in this video, I'd like to talk about geometric dimensioning and tolerancing and your first article inspection for your CNC mill project 1 and your CNC lathe project number 1. Now, so far, you've really been exposed to conventional dimensioning practices when you were building your mill project 1 and your lathe project 1. Well, on top of conventional dimensioning practices, there's two GD&T callouts on that mill project 1, or one on the mill project 1 and one on the lathe project 1, that are going to introduce you to the world of geometric dimensioning and tolerancing. And really what GD&T is, it's a collection of symbols, or there's 12 of them, and they're basically applied to your drawing as a note, and it allows you as a mechanical engineer or the design engineer to specify your design intent. So you're able to locate datums or perfect surfaces that you want to act as 0 points and you want to measure off of. So you can specify surfaces that you want as datums or that you want to measure off of. You can go ahead and set up features and locate them specifically off certain planes or datums as well, and basically explain all of the critical part features that are important to your design by using this collection of notes. So really what GD&T is, it's a way of engineers communicating their design intent. And this can be done only one way on an engineering drawing. The only way you can specify a geometric dimensioning and tolerancing callout is in something called a feature control frame. Now you'll see right here on the screen, this is a feature control frame. So all it really is a box that holds your GD&T callout in the first compartment. So for this example here, you'll see there's position. And after that, it gives you the tolerance zone size. For this example, it'd be 0.000 or 0.005, held at maximum material condition. You kind of see that up here. I'm just going to point up here. Then we have any of the datums, the primary, secondary, and tertiary datums that callout will relate to. So all a feature control frame is a box that specifies the GD&T tolerance for that feature right there. So it's the only way GD&T symbols can be applied on a drawing is in a feature control frame. There we go. Now, you're wondering, what are these GD&T symbols Mr. Giorgio keeps talking about? Well, GD&T has 5 different types of tolerances. There's form, profile, orientation, location, and runout tolerances. Now, if you look at it, the form tolerances are for individual features. That means they don't relate to a datum, which is a perfect line or surface. They just go ahead and specify a certain form a feature must have, like how straight it is, how flat it is, how round it is or out of round for circularity, how perfectly cylindrical the feature is. Those are really the 4 major types of forms that you can have. You can either be straight, flat, round, or cylindrical. Now, after that, we have profile tolerances. So remember, the world's made out of a bunch of lines and arcs. It's what everything's made out of, a line or an arc. And a profile tolerance will set up a perfect profile that the feature has to fit within. And you inspect to make sure that the outside surface of that profile falls within that boundary. We're not going to do profile tolerances in this class. We're going to learn a little bit more about orientation tolerances, and we're going to do some form and orientation inspection on our parts. But what orientation tolerances do is they allow you to orient a part either parallel, perpendicular, or at some angle. So you can orient features 3 different ways in mechanical engineering. You can either be parallel, you can be perpendicular, or you could be at some certain angle. So that's how orientation features work. Now, there's location tolerances as well. We're going to talk about those a little bit more just to show you why they're advantageous for a mechanical engineer to use a low positional tolerance over a conventional one. But location tolerance is actually shrunk down to 1 type. Concentricity and symmetry left in 2018. And the ANSI, or the ASME ANSI Y14.5 rules. So there's no longer concentricity or symmetry to locate things. You just use positional tolerances to locate everything. We'll talk about that more in a minute. Then last but not least, if you have something that's going to be rotating, you will look for the amount of runout that it has. It's how much basically it differs from the central axis of rotation. So it's kind of checking circularity and how well the part is balanced about its point of rotation. So that's what runout's all about. We're going to go ahead and talk about form, orientation, and location tolerances for the rest of this lecture. We're not going to worry about profile and runout for today, for this class. Now, moving along, you're going to see, we're going to first talk about why location tolerances or positional tolerances are more advantageous in mechanical engineering to use compared to a conventional tolerance. Then we'll talk about the first article inspection for our mill project 1 and our lathe project 1. But a locational tolerance, there's really only position left. So position and location are the same thing. They're going to locate the feature off of a perfect surface or plane, which is known as a datum. So positional tolerances measure how much how much you vary from a zone called true position or a location called true position. True position is the theoretical exact perfect location of that feature. So it'd be if we were to take the solid model, the features are all made in true position on the solid model. But when we go to manufacture that, nothing's perfect. We'll slightly be off of true position ever so slightly every single time. Maybe 1 or 2 parts will hit true position perfectly, but you can't do that in mass production. So why we like to use positional tolerances in our mass production is that it gives us a larger tolerance zone to hit or to be good within. And so when we have conventional tolerances, you get a rectangular tolerance zone. And that rectangular tolerance zone isn't going to be as accurate as a round tolerance zone or a circular tolerance zone. So if I use a circular tolerance zone, I'm going to be able to improve the interchangeability of parts while increasing my manufacturing flexibility. So I'm going to have more parts that are going to come out good and within tolerance because I have a larger tolerance zone with a positional tolerance than I would with a conventional tolerance there. Also, another thing with a positional tolerance is my tolerance for my zone that my part has to lie within can get larger as my feature departs from the maximum or the least material condition. We're going to talk about that here in a second too. So let's first talk about why a true position tolerance zone, which is a cylindrical tolerance zone or a round tolerance zone, gives you more area than a conventional tolerance one. So when I'm saying true position is the center line of the hole where it should truly be. Then our tolerance, if we were to make a bunch of these parts, if, let's say we make 100 of them, we want the center line of that hole to lie within this zone here. And that's really our true position zone that we have right there. Now, to do that, a conventional drawing gives you dimensions off the corner, like 12 plus or minus a certain amount. Let's just say 12 plus or minus 0.25, because that's what this is doing right here. 12 plus or minus 0.25. So if it's plus or minus 0.25, that gives us half 0.5 up or 0.25 up, 0.25 down, right? So we have basically a 0.5 rectangular box if I'm using conventional dimensioning just off the edges of a part. Well, let's say we make this part, then we put the center of the circle right here. The part's still good. Then we make another one, we put the center of the circle right here. The part's still good. Then we make another one with conventional dimensioning and put the center of the circle right here, the position of it. Well, in conventional dimensioning, that's outside our positional or outside of our tolerance zone. So this spot right here would be a bad part, even though the center of the hole would be closer to true position than it would be if it was made right here. So what positional tolerances do, they recognize that there's all this area right here outside this square tolerance zone that if we put the center of the hole, the part should still be good. So if I put it out here and make a circle, you'll see that's what creates the diameter of the circle. So I figure out the hypotenuse of what my conventional tolerance zone is, and that's the size of my circle. So now my 0.5 by 0.5 square tolerance zone actually becomes a 0.7 diameter tolerance zone, giving me 54% more area to manufacture the features within. So it's giving me more area to produce the features in on the part, making more acceptable parts past quality control, and more parts still fit together. So it's a way of it's a win-win for manufacturing and design. Now, when I have a positional tolerance specified on my drawing, I actually don't have dimension, or I don't have tolerances on my 12. I have something called basic dimensions. And the way this works is I have my size up here. So remember, everything needs a size and a location. And I have my location right down here. So I got my size and my location. Location's the same as position. Now, these basic dimensions locate where the true position off the datums for this tolerance zone needs to be. So this tolerance zone is 0.7 when it's at maximum, when the size is at maximum material condition. So that means I have a 0.7 diameter circle that I've made right here that part has to fall within. Now, when the hole is at its maximum material condition, that means it's going to have the maximum amount of material. It's at its smallest size. So when I'm at 14.5 for my hole size, that's at MMC. So my tolerance zone size, I'm going to write zone over here. Zone size at MMC is 0.7. Well, the thing is with positional tolerances, as I can hold them tighter at a material condition, like maximum material condition when the hole's the smallest, but as the hole gets larger, I can actually add the amount that we depart from that material condition to my positional tolerance and be off a little bit more. So what I can do is if I produce this hole and it's at 14.5, my zone size is 0.7. But if I produce one of these holes at 15 millimeters, my zone size would be actually 0.13. So the zone that the feature can fall within can actually get larger as I depart from the maximum material condition. So in a way, I've got dynamic tolerancing too. So as my hole gets larger, it can be off a little bit more and still have the parts fit together. So this is another way positional tolerancing can really add to cut down the scrap that you have in your shop, because we're now using that round tolerance zone and we're allowing it to get bigger as the hole gets bigger by holding it at a material condition. So positional tolerances give you a round tolerance zone. They use basic dimensions to locate the tolerance zone, and then the tolerance zone can change size based off the material condition you actually place in there. So that's why it's so beneficial, and why Larson talks about GD&T and positional tolerances, why I talk about it, why Mr. Pols talks about it. It's used out there heavily in industry when dimensioning parts. Now, if you were to convert a conventional to a positional tolerance, all you got to do is just change the location dimensions from plus minus dimensions to a basic dimension. So the dimensions with the boxes around them, they're basic dimensions. You would then add that feature control frame, which is how you specify GD&T, to the diameter dimension. And then you add any of the datums wherever you want to measure off of. You'll end up then with your feature control frame. So if you notice, this feature control frame right here, it's position. This is the tolerance and where it's held at, maximum material condition. The feature is perpendicular to the primary datum, so this is primary. This is secondary and tertiary, so 2 and 3 and primary. So your feature is always perpendicular to the primary datum, located off of B and C. So B datum and C datum are where it's located off of. A datum is where the feature is perpendicular to. And that's really how positional tolerances work. So I have my position right here, and I have my size for my feature. And all these basic dimensions do is just show me where the true position or the true location of that hole really should be. Now, for your assignment, you're going to be doing a virtual first article inspection. I just want to talk about a couple things now. So you're going to be going through, and there's pictures of us measuring the part. In fact, there's a video talking about parallelism and how to do this parallelism inspection. You're going to go through and watch that video right after this video. So, but looking at it, we have our title block here. Our title block gives us all the tolerances right down here unless the dimension specifically has one on it. So when I look at this, I see that this 0.48 is a two-place dimension. Down here, two-place decimals are plus or minus 10 thou. So if I was to be asked for the limits of this dimension, the limits are 0.49 to 0.47. So that gives me the limits there that feature, once I manufacture it, has to be within. It has to be between that tolerance. So your assignment is going to ask you questions about the first article inspection. It's going to ask you to identify features. So for example, A, if I look here, overall width, I see A is this length. I go back to my drawing. I see my length is 4.0 with 3 decimal places. And 3 decimal places are plus or minus 5 thou. So my target dimension for this one would be 4.0. Make sure you put the right amount of decimal places. And my limits would be 4.005 to 3.995. So that's my limits dimensions. It gives me the maximum and the least amount of material that that feature can be. Then you're going to read the caliper in the assignment or whatever's measuring, and you're going to write down a measured value and whether that passes or fails. So that's how the conventional dimensions are measured for mill project 1. Now, on that drawing, there is some GD&T, geometric dimensioning and tolerancing. In fact, we have parallelism right here in this feature control frame. So we have this feature control frame. We have to be parallel within 3 thou to the A datum. So what that means, when I go back to my drawing, when I look at my drawing, the bottom surface is the A datum. That's what we put down on the granite surface plate. We then want to make sure, so we put the bottom of the part down on the surface plate right there. You'll see it in the video that's coming up. You then use an indicator. Let me go to the next slide. You use an indicator to zero it out like you see right here. And this whole top surface has to be parallel within the bottom surface within 0.003. Well, looking at the conventional dimensions, C can be anywhere between 0.49 and 0.47 like we talked about right there, right? Well, if I was to make that at 4.9 to 4.7, I'd have a wedge, kind of like that. Now, once I make it anywhere between 0.49 and 4.7, this top surface, this GD&T has modified it even more, that top surface has to be parallel within 3 thou. So to get this surface parallel with this surface, I sweep the indicator across it, and I look for the total range of indicator displacement. So if I go down here 1 tick mark and 1 tick mark, or 2 tick marks this way, I basically have moved 1.5 thou. Each tick mark is worth 0.0005 or a half a thou. So my total indicator movement, positive to negative, if it moved 3 tick marks, I'd be at 0.0015 for the actual parallelism measurement. So moving back to my first article inspection, if I was to be asked here about surface parallelism, your target would be 0. If you had a perfectly parallel surface, the indicator would not move, it would just stay at 0. And your limits are between 0 and 0.003, because the indicator can move anywhere in between that. So you'll watch the video and see how much the indicator moves to get your measured value for the assignment for mill project 1. Now, if you have any questions about this assignment, stop by my office hours and I'll definitely help you out. Now, lathe project number 1 inspection has some GD&T on it. It's right here. It's a form tolerance. It's called circularity. So when I manufacture this part, I have a 925 value right here. That means 3 decimal places plus or minus 5 thou. So I could be anywhere between 930 and 920. for my sizes. Maybe I measured one right here and it's 920. I measured one right here for the diameter, it's 930. My part would still be good unless I specify GD&T. So once I have this size tolerance here, and I make it in between the size, my GD&T has to be a tighter tolerance. So you'll see once I make it, I have to be circular within 3 thou. What that means is I've set up 2 parallel cylinders, and the indicator can't move more than 3 thou, the distance between them. So what I end up doing is I put it on a V block. Because if you think about it, you've been to statics, a lot of you. When you have a reaction force here, you have a single normal force, a single normal force, and the indicators are third point touching the part. When we zero out the indicator on the top of the part, we actually rotate the part here, and we look for the amount of total indicator movement back and forth to see how circular we are, or to see how out of round we are. If I had that egg shape that I talked about between 920 and 930 in the diameter, I would see a lot of movement on this indicator. However, if I had a perfect circle, which you should because you made it on a lathe, I would see 0 movement on this indicator, and it would stay at 0 the entire time. So that's what I've got for GD&T on our lathe project. We're going to inspect circularity. Now, looking at it, you can pretty much get most of these target dimensions here in the limits. Remember the limits, the upper and the lower value. And then for the circularity, if you remember, 0 is our target, and between 0 and the tolerance point 0.003 are our limits. And that's going to be the difference between conventional dimensions and GD&T. So to kind of recap it, GD&T, let me go back to the symbols, is a collection of symbols that we can apply to features on our part to communicate design intent. As engineers, we can go ahead and specify what surfaces are our datums, or the most important surfaces to base measurements off of. And what surfaces of that part, or what features on that part need to be perpendicular or parallel to each other, or which ones need to be really round, so we maybe do circularity, or which ones need to be located very accurately, so we'll do a positional tolerance and give that bonus tolerance to our manufacturing engineers when they make it. So GD&T is going to save you time and money when manufacturing, especially money when it comes to the quality control stage of things, and being able to communicate that design intent as an engineer. So I know you'll learn more about it in Larson's class, your ME 251, and if you haven't already been to that class. If you have any questions about GD&T, you can definitely stop by my office hours or shoot me an email. And now don't forget, you got to go ahead and do those first article inspection assignments that are the virtual ones for 143 Lab this week, or the IME Freshman Machining Lab series. And don't forget, there's one more video showing how we inspect the GD&T callouts on our mill part and our lathe part. So watch that video before you do the assignment, and have a great day. Bye.